This lesson is pretty much going to be a straight continuation of the last one, because while we just previously talked about horizontal projectiles, projectiles that are launched with a velocity that is perfectly horizontal, that's very rarely going to be the case in the real world, because more realistically, we're going to have projectiles launched at an angle. And what we're going to really quickly find is that everything we've already learned still applies. This is really just taking it one step further. So before we start going into the details, let's remember something very, very important. That the horizontal motion of an object is independent of the vertical motion and vice versa. In other words, how this projectile travels, as we can see here, this is launched at an angle through the air in this arc. Its horizontal or side-to-side motion has no effect on how it moves up and down, and how it moves up and down has no effect on how it moves side to side. Now we're going to do a problem that will show us all these details in a second, but let's really focus on trying to get the conceptual ideas down of how this is very closely linked to horizontal projectiles and to other elements like free fall that we've already learned about. Well, first off, let's examine the velocity vectors of, for instance, this cannonball, as this cannonball goes through the air and eventually returns back to the ground. So, let's say it has some initial velocity v. And you'll notice that v is in the direction of the arc, because that is the direction the cannonball is moving. But, unlike in, I should really say this is really the initial velocity, unlike in horizontal projectiles, where it was completely horizontal, we now see we have Vx naught, that's supposed to be a naught, there we go, and Vy naught, the initial horizontal and vertical velocity. And we find those just by doing the components of the v vector. You can find the horizontal component, how much the cannonball is moving to the right, and the vertical component, how much it is moving up. And we can treat those independently like we just discussed. So the velocity in the x direction, because gravity does not go that way, is going to be equal to continually what it was initially. So it is going to be a constant value. This Vx naught is not going to change the entire time the projectile is in the air. But Vy, we know as it goes up, it is going to slow down, stop for an instant, and then continue to speed up in the opposite direction, specifically with regard to the vertical. So let's look at a few different moments in time and look at the vectors in a little bit more detail. So how it moves from this initial position to this next position, we see that it goes there with velocity v that we can v naught, that we can break down into the x and y components. We will now redraw the three vectors. Now a reminder, Vx naught is equal to Vx, so these are exactly the same. And it's a little hard to tell, I didn't make this very dramatic, but Vy is a little shorter than Vy naught here, because it is starting to slow down going up due to gravity. So we go to the next instant in time, same thing happens. Vx is the same, Vy has gotten a little smaller. If we were to add these tip to tail, for instance, if I was to draw Vy here, we would see that this v is the resultant vector, that is its total velocity as it goes up. One more time, we go up a little more, v's gotten even smaller, until we get to the very top. Now, an important thing here is that I said it stops for an instant, but that is only in the Vy. The projectile at the top still has horizontal velocity, and at this point it is entirely horizontal. And actually, from this point onward, we can pretty much treat it exactly like a horizontal projectile, because now it's going to continue to have that horizontal velocity, but the vertical velocity is going to speed up. It's going to go faster and faster and faster in that direction. It's going to get bigger, and these vectors are going to get longer and longer and longer and start to push more downwards. But what about the acceleration vectors? How exactly is this accelerating? Now remember, we're only looking at the instant after it has left the cannon and before it hits the ground. And if that is the case, we know that the acceleration this object is going to experience, one, there is no acceleration in the x direction. It does not accelerate side to side because gravity only acts downward. So the only acceleration on the cannonball will be g, 10 meters per second squared, down. Now you'll notice I didn't write a little y on here, and that's because this is the entire vector. Since there's no x component, a is equal to ay. They're the same thing here. And if we look throughout the different points in time, the acceleration will always be downward. It slows down as it goes up, because then the velocity and up acceleration is down, they're opposite directions, so it slows down initially. At this point, it stops in the vertical direction and changes direction, and then it starts to speed up as it goes back downward. So just like how we learned about horizontal projectiles, let's look at a problem and discuss a strategy we can use to solve it. So a cannon fires a cannonball at 100 meters per second, as we can see with V0 here, with a launch angle. So when we say launch angle, what we're really saying is this angle with the horizontal. It's basically how much is the cannon tilted up when it is fired, of 50 degrees relative to the ground. So we have 50 degrees here, 100 meters per second. And the questions we want to answer are, how far away will the cannonball land from the cannon? And how high is the peak of the cannonball's trajectory? In other words, we want to know the total delta x, and we want to know delta y specifically at the top. How high does the cannonball go? Now, one brief thing I want to note here. You might look at this and go, well, the cannonball may not be fired from exactly ground level. Unless you are told otherwise, we can go ahead and assume that this little distance between the ground and the top of the cannon is so small that we can ignore. Now, occasionally, you'll be told you cannot do that, and you'd have to be given more details. But as of right now, we're going to pretend that this is being fired from a position of y equals 0. That it's being fired from the ground level. Well, this should look familiar, because the strategy for solving problems with projectiles launched at an angle is literally identical to the strategy for solving problems for horizontal projectiles. There's really only going to be one key difference. First, we still want to identify the givens and unknowns and separate them into a horizontal and vertical column. That is nothing new. Remember, we still want to treat them independently of each other. Typically speaking, for most of what we're going to be doing, you're going to want to use the guess method in one dimension or the other to solve for time, and then you're going to use that time and plug it back into the givens of the other dimension, since time is the same in both dimensions, and you'd find whatever you want to know, whether that's delta x, delta y, vx, vy, whatever. Now, the real big difference, though, here is that we have these two equations that I said more often than not are going to be the equations you use. Always, not necessarily, but more often than not. But the thing is here, though, is previously, now we said that we could simplify the delta x one because there is no acceleration in the x direction, so that whole piece goes away. So we really just have this. But now, unlike previously, we actually do have an initial velocity in the y direction. So this no longer goes to 0. We need to actually include the whole equation, or else we are not going to come up with the right answer. So let's look at the first question being asked. How far away did the cannonball land? In other words, we want to know the cannonball's range. It's delta x. So let's start identifying the givens and unknowns for the horizontal and vertical dimensions. I went ahead and wrote them out here, but let's talk about them. So in the horizontal direction, we have the initial horizontal velocity is going to be equal to, I should say this should be equal to the, there we go, the horizontal velocity at any point in time, which we'll notice, though, is not going to be 100 meters per second, because this v is in both the x and y dimension. So we need to solve for the horizontal component of x naught, which would be 100 cosine of 50 degrees, because it is adjacent to 50 degrees. And if you take your calculator, you plug that in, you're not going to do that in your head, you get about 64.3 meters per second to the right. Additionally, we know the acceleration in the x is equal to 0. The unknowns we have are time and delta x. Now let's look in the vertical dimension. Well, rather than finding the horizontal component of the initial velocity, we now need the vertical component, because this is not going to be 0 here, because it's not horizontally fired. It is being fired up at an angle, so we actually do have an initial vertical velocity. And it's going to be 100 sine of 50 degrees, this vertical component, which if you plug that in your calculator, you get about 76.6 meters per second up. Now the acceleration is 10 meters per second squared down, and because we're looking from the point where it leaves the ground to when it returns to the ground, remember we said we can go ahead and treat this as y equals 0, the delta y will be equal to 0. And the only unknown we therefore have is time. So I've gone ahead and rewritten the horizontal and vertical givens and unknowns here. And if we look, what we're looking for is delta x. And we don't really have three useful givens here, so instead let's find time in the vertical direction, and then we will stick this number back in over here. So to find the time, we are going to use this equation right here, delta y equals vy naught t plus 1/2 at squared. Now, something we can remember is that because this is 0, we can go ahead and say, oh, let's go ahead and write that down to 0 to simplify this just a little bit. So if I do that, I end up with 0 equals vy naught t plus 1/2 at squared. Well, I can now divide every piece by t. We've done this previously. So let's go ahead and do that now. And when that happens, these t's are going to go away. That's just going to stay 0. And the squared is going to go away. So I get left with 0 is equal to vy naught plus 1/2 at, which I was going to solve. I could say t will end up being what? It's going to be negative 2 vy naught. I'm going to subtract the vy naught across, times by 2, divide by a. And I get something that looks like that. And in fact, that is the equation we get. So I'm going to go ahead and stick in my givens. And I have negative 2 times 76.6 divided by negative 10. So I went ahead and assumed that up is positive and down is negative. And I stuck in my positive because it's up and my negative because it's down. And you get 15.3 seconds. Remember, you have to be very consistent with these up or downs. This is especially important with projectiles launched at an angle because now we're definitely dealing with an up and a down. With horizontal, you're really just dealing with one. But now they're dealing with an up and a down. If you get them mixed up, you're going to get in a lot of trouble. So we have, therefore, 15.3 seconds. So I'm going to take this number and move it over here, and I now have a given of 15.3 seconds. So I can use this equation now, delta x equals vx naught t plus 1/2 at squared, but we know that the acceleration in the x is 0, so we can eliminate that piece. And I can therefore just plug in delta x equals our initial velocity in the x, 64.3 meters per second, our time 15.3 seconds, and we get a range of about 984 meters. So that would be how far the cannonball is going to go. Same process that you've done previously. The only real difference is we now have an initial velocity that we have to account for. So now let's try to answer this second question. How high is the peak of the cannonball's trajectory? So in other words, what's the highest that it goes throughout this entire path? Now initially you might be a little concerned because we can no longer use delta y equals 0 like we did previously, so how can we know some of these details? There's a few different ways you could do it, but the really important thing we want to get here is that the vertical motion is exactly like a projectile being thrown straight up and down. So what I want you to imagine is just like last time. Let's imagine you're like standing over here and the cannonball's coming at you. Okay, now, granted, you don't want it to come directly at you, but we can say you're a little further back. And if you were facing towards it and it was coming straight at you, the cannonball would appear to go up and then go down as it comes towards you. And so it would actually resemble this straight up and down motion, just like how a horizontal projectile straight head on looked like something dropped. We're just now adding the up and down part to that. So we can solve this just like we solve a straight up and down motion, because this only really involves the vertical part of the trajectory. We don't really care about how far it's gone. That's totally independent of this. We only care how far it goes up and down. So if I look at my givens, I'm just going to look at the vertical ones. I have a vy naught, once again, of 100 sine of 50 degrees, which is 76.6 meters per second up. I have an acceleration downward of 10 meters per second squared. And at the top here, it is going to stop for an instant in the vertical direction. So Vy is 0. And I need a t and I need a delta y. But I don't care about time. Though granted, in the previous problem, we found the time for the whole trajectory. So if you wanted to, you could cut that time in half. And due to symmetry, we would know that however much time it went up this way was the same amount of time it took to go that way. So we could simplify it like that. And you could really just do it that way. But we're looking for delta y. So we're just going to go with this method. I'm going to use this equation, Vy squared equals Vy naught squared plus 2a delta y. Now remember, because Vy is 0, we can get rid of that piece. And we're going to go ahead and solve for this. I'm going to move that across. And just put this here, but we could just make that 0. There we go. I'm going to put that part across, and we're going to divide by 2a. And when you stick in the numbers, we get 76.6 squared over 2 times negative 10, or about 293 meters up. For the sake of practice, I'm going to go ahead and give you one more problem to do right here on your own, and then you can come back and see how you did. So what we have now is a little bit more complicated situation. A cannon is located on a ridge that is 30 meters off of the ground. So the cannonball is being fired at 30 meters in the air. It fires a cannonball at 80 meters per second with a launch angle of 37 degrees toward a ridge that is only 5 meters off the ground. How far away does the cannonball land? In other words, what is the range, the delta x, of the cannonball's motion? So if you want to give this a shot, but go ahead and try it, then come back and we'll discuss it all together. Well, hopefully you tried it on your own, but let's go ahead and go through the details to make sure you feel okay about it. I went ahead and wrote all the givens and unknowns here. So, my givens, I know the acceleration in the x is 0 and the velocity of the x is constant, and it's going to be 80 cosine of 37 degrees, so that's the adjacent side, or about 63.9 meters per second when I stick that in my calculator. Don't know time, don't know delta x. In the vertical direction, I know that the initial velocity in the y is 80 sine of 37, because that is the opposite side, which is about 48.1 meters per second up. Remember, this up is important. The acceleration is 10 meters per second squared down. And my delta y, now this is tricky. It was 30 meters up, but it landed at 5 meters above the ground, so that's going to be about 25 meters, this is super important, down. It is going to land 25 meters down from its current position. If you forget this, you're going to be in a lot of trouble. You have to remember that piece, or else your math's not going to work out. And the unknown is therefore going to be time. Once again, I wrote out all my givens here, and we're looking for delta x. That's a pretty good clue. We should find time in the vertical, and then stick it across. So if we're going to do that, I'm going to use this equation here that we've been using pretty continually. Delta y equals vy naught t plus 1/2 at squared. However, I cannot make this 0 like it's been previously because we now have a delta y. So in fact, how do I go about solving this? Well, I'm going to move it to the other side, and I went ahead and rearranged this a little bit because I'm trying to find t, and what you will notice is I can't get rid of the squared anymore. And we're going to have to go down a little bit of a trickier path, because if I go ahead and stick in my numbers, I have negative 5t squared, that's 1/2 times negative 10, plus 48.1t, plus 25. This is crucial, because it was down. I went ahead and said down was negative, up was positive. That means since it's minus delta y, this will be plus 25. Well, unfortunately, you're just going to have to kind of bite the bullet here, and you're going to have to use the quadratic equation, which is, you probably know it from your math class, but it's basically going to be a negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Very easy to mix up your positives and negatives here, so be careful. If you have a solver in your calculator, it's okay that you use it. You just have to make sure you're doing it properly. And when we get numbers, you'll see that you get two answers, because quadratic equations have two answers. You get negative 0.49 seconds and 10.1 seconds. Well, because one of these is negative, we know it can't be that. We did not go back in time as the cannonball was fired, so it must be 10.1 seconds. So I'm now going to stick this into my other side, the horizontal side. The time is 10.1. I'm going to use the equation we typically use. This part goes to 0 because the acceleration in the x is 0. Plug my numbers in, and we get about 645 meters. Done. So what are our main takeaways for this lesson on projectiles launched at an angle? Well, it's very similar to the takeaways you had for horizontal projectiles, just extended a little bit further. One, can you describe and draw vectors for the horizontal and vertical motion for projectiles launched at an angle? So keep that in mind. So for the velocity, it's going to shrink as it goes up and grow as it goes down. But in the horizontal dimension, it is always constant. And in the vertical dimension, it's going to be big, get smaller, go to 0 at the top, and then get bigger as it goes down. And acceleration is constantly 10 meters per second squared down. Additionally, can you employ a strategy to solve problems involving projectiles launched at an angle, including situations involving multiple elevations? Once again, identifying your givens and unknowns for both horizontal and negative, keeping in mind you now have an initial vertical velocity. Solving for time in one dimension, sticking it back in, and finding the unknown that you want.